Welcome everyone to our June seminar. My name is Sumit Roy. I'm an assistant professor research in the Department of Engineering at Durham University. This event is organized through the EPSRC Network Plus for decarbonization of heating and cooling, and is part of a series looking at the different challenges of decarbonizing our heating and cooling sectors and behaviors. This month, we are hosting two speakers to explore the challenges and strategies for the decarbonization of heating and cooling. Our first speaker today is Professor Yunting Ge, who is a professor of building service engineering at London South Bank University. He has more than 20 years of research and development experience in energy conversion technologies, hydrogen energy and storage, refrigeration, heat pumps, and built environment. Professor Ge received his PhD from Department of Thermal Engineering at Tsinghua University, China. He obtained an MSc and BSc from the Department of Mechanical Engineering at Jiaotong University, China. He's going to talk about Hydrogen Heat Project, which is investigating strategies for a novel concept of decarbonizing district heating and cooling system using the integration of metal hydride heat pump on site, long distance hydrogen and heat transport, and metal hydride heating and cooling for end users. Over to you, Professor Ge.
Sami, thanks for your introduction. Okay, good afternoon, everyone. Thanks for attending my presentation. The title of my presentation is Characterization of Metal Hydride Alloys for Application in High Temperature Heat Pumps. And this is part of the 3 years EPRC funded project, which is collaborated between London South Bank University and Brunel University. My name is Yunting Ge, and my researchers, Xin Yu Zhang and Ping Yu Huang, we come from London South Bank University. And Professor Savas Tasso is from Brunel University. And first, I would like to outline the background and research objectives of this funded project. As we know, in the UK, heat accounts for over 1/3 of the nation's greenhouse gas emissions. For the cooling, global warming is also increasing cooling demand, which globally is now the fastest growing end-use energy demand in buildings. And to meet ambitious target of net zero by 2050, it's essential to decarbonize the provision of heating and cooling. To achieve these targets, we need to maximize the utilization of renewable energy for the energy supply, and also recover as much as possible for the industrial waste heat for the heating and the cooling purpose. Accordingly, there are 3 research objectives and methods which are listed in this slide. Firstly, we will investigate the waste recovery from industries with temperature range between 40 and 230, and to recover it to obtain the temperature, the usable heat with a temperature of 100 degrees C. We are using some advanced heat pump system. Later on, we'll introduce about this. And the second objective, once we have recovered the heat with temperature about 100 degrees, we will transport this recovered heat through long distance by using of hydrogen technology to the end user. And at the end of user, we convert this recovered heat to use for heating and cooling for buildings. And the first part of this project is on waste heat recovery from industrial site with temperature between 35 to 230, and with advanced heat pump technology to obtain heat source with temperature about 130 degrees C. So we will utilize innovative heat pump technology system. We call it metal hydride heat pump, to recover this medium and low temperature heat source to get the heat output of temperature 130 also. And comparing to other heat pump technology, such as compression and absorption heat pump, And the mitohydride heat pump system has its own advantages. This includes low electrical power input, environmentally friendly working medium. We are using hydrogen as a working medium. And the whole system is more compact techniques compared to the absorption heat pump system. And more importantly, and through this heat pump system, we can obtain relatively high temperature heat output, such as, which is about 100 degrees C, which is difficult to obtain by the compression and absorption heat pump system. But there are some challenges in this heat pump system. One is to identify and mitohydride alloy so that it can be efficiently used in the mitohydride heat pump system. Another thing is to characterize the mitohydride alloys identified so that the characterization result can be efficiently utilized for the further experimental and theoretical analysis for the mitohydride heat pump system. And also experimental and theoretical analysis for the proposed mitohydride heat pump system. To enable this, to address these technologies, so in this project, we have designed and will develop a test rig for the mitohydride heat pump system. And we have already identified mitohydride alloys from our previous presentation. And in this today's presentation, I will report some progress and research outcome for the characterization of the mitohydride alloys, which are used in the high temperature mitohydride applications. And also by utilizing the characterization result, we will explain about some simulation result for the mitohydride heat pump system. And I would like to briefly introduce the mitohydride, the system of the mitohydride heat pump. So in this slide, the left is the schematic system layout, and the right side is the mitohydride heat pump system cycle. As you see from the system layout, the system consists of two identical mitohydride alloys, and one is operating on the high pressure side, and another part is operating on the low pressure side. And the connection pipe of hydrogen is connected between two mitohydride alloy reactors. One is high temperature mitohydride reactor, and one is low temperature mitohydride reactors. And you can also see there are two heat sources, one with temperature TH, one is temperature with TL. So one we call it high temperature heat resources, one is low temperature resources. And also we have one temperature TM heat sink. So this heat source and the heat sink will be connected to different mitohydride reactors. So the whole system cycle consists of two identical half cycles. And the first half cycle, so in this slide, is described as a solid line, and the second half of cycle is depicted with the dot lines. So for the first half cycle, as you see from this slide, the high temperature heat source is added to the one high temperature heat mitohydride reactor, and the hydrogen will be released from the reactor to flow to the low temperature reactor MHH2A, where the heat is released to the medium temperature heat sink so that we can obtain the heat output with medium temperature. And on the low pressure side, the low temperature heat source will heat up the low temperature mitohydride reactor, and the hydrogen will be released and absorbed by the high temperature, another high temperature mitohydride reactor, and the heat will be released to the medium temperature heat sink. So for the second half of the mitohydride heat pump cycle, and only the heat source and the heat sink will be transferred to different mitohydride reactor, and the whole cycle will be repeated. So the heat output will be continually produced. And you can also see from the cycle diagram, you can see the temperature range. For the high temperature, the temperature range is between 180 to 220 degrees C. And the low temperature range is between 25 to 45. And the heat output temperature is around 130 degrees C. correspondingly, we have designed a test rig for this project, as shown in this slide. And this test rig consists of two metal hydride reactor. One is the high temperature metal hydride reactor, we call it MH1, and this is a low temperature reactor, we call it MH2. And these structures are connected with a hydrogen pipe. Along the hydrogen pipe, you can see a number of valves and flow meters, and some safety valves, and also the temperature and the pressure measurement devices. And above this hydrogen connection pipe, you can see three components. One is electrolyzer, which is used to produce the hydrogen for the test purpose, and also one vacuum pump, which is used to vacuum the whole system before the hydrogen is charged. And also there is a hydrogen vessel, which is to store the excess hydrogen for the system. And for the heat transfer side, you can see three thermostatic buses, that one, two for heating, one for cooling. And by means of four three-way valves and the heating source and the cooling system, cooling equipment can supply and cool the metal hydride reactors in the system. So the whole system will be controlled automatically, so that the whole system can operate continuously. So far we have received old components for this test rig, and the whole test rig will be assembled by a manufacturer, and the whole test rig will be ready, I think, hopefully by end of September. On the right side, you can see a picture. These are two reactors, MH1 and MH2. We have designed these two metal hydride reactors, and also they have been manufactured and will be installed in the whole test rig. So from I think previous presentation, and we have identified two metal hydride alloys. One is for the high temperature reactor, one is for the low temperature reactor. And based on the thermodynamic analysis and also the performance calculations, and we selected these two metal hydride alloys from about hundreds metal hydride alloy pairs. And we think these two metal hydride alloys are suitable for our high temperature metal hydride heat pump system. So detailed information about how to identify these two metal hydride alloys can be found from my previous presentation and our relevant publications. And so the quite important step is to characterize the metal hydride alloys, which can be efficiently utilized in the proposed high temperature metal hydride heat pump system. And here we just saw a diagram. This is called the PCT Phase diagram. It's quite similar to the referent thermal properties shown in a pH diagram. So as you see from this PCT, P is pressure, C is concentration, T is the temperature. So you see from the PCT Phase diagram, and the y-axis is the pressure, and the x-axis is the concentration of hydrogen. And you can see a number of lines, solid lines, that indicate the isothermal temperatures. And also you can see a dot line here. This is transitional, we call it transitional dome curves, that one. And what you can see from this PCT phase diagram, and the whole diagram is divided into three regions. We call it alpha plus beta, and beta, depending on the hydrogen absorption process in the metal hydride reactors, that one, yeah. So, and these two regions are divided by this dome, transitional dome curves. And on the top of the dome curves, I think there is a critical point, that one, yeah. So what you can see here, when you do for the hydrogen absorption set in the process in the metal hydride reactors. So a little bit hydrogen absorption, you can see there is a substantial pressure increase. Similarly, for the beta region, so a slightly increase of the hydrogen absorption in the metal hydride reactor. So there is a substantial pressure increase. For the in the middle, for the alpha plus beta region, this region, and this is what the metal hydride heat pump operating at. So a larger, you can see what you can see, a larger hydrogen absorption. You can see there is a quite small pressure increase, that one. And also the changing rate of the metal hydride absorption is depending on the temperature of the opening temperature. So the higher the opening temperature, the lower the smaller of the hydrogen absorptions. And on the top of the critical point, so you can see the absorption hydrogen capacity, hydrogen storage capacity will be close to zero, that one. So this is quite an important step before any experimental and theoretical analysis. We need to correlate and also correlate the we need to set up the correlation model for each region of this phase diagram so that we can draw the PCT phase diagram, and we can find out at any temperature and hydrogen concentration, we can immediately find out the pressure. So that will be quite helpful for the theoretical analysis, for the modeling development, and also can direct correctly for the experimental investigation after this. So in this project that want to achieve this target, so we have developed correlation models for each region of this PCT phase diagram, alpha, beta, and alpha plus beta. And also we get the correlation parameter based on some limited experimental data from literature. So if you want to obtain the overall phase PCT phase diagram from only the experimental investigation, experimental investigation or experimental measurement, that is not possible, because each isothermal line, so in this diagram, will require about 1,000 measurement points. So that is not possible. So I think the best way to obtain a correlation model based on some limited experimental results, so that the correlation model can predict the overall areas of the whole PCT phase diagram. This is what we have done so far in this project. So we're using different formula to correlate the different areas of the PCT phase diagram. For the alpha plus beta phase region, that one, we're using the formula 1 as a formula to correlate the model for this region. What you can see from this formula is applied for both absorption and desorption process of hydrogen. And what you can see from this formula, there is a variable pressure and temperature and also concentration. And also you can see some constants, including the reaction entropy, and also the mid value of the hydrogen concentration, and also the flow slope of the hydrogen in the alpha plus beta region. So we have this formula. If we know some limited measurement data, so we can correlate it out this constant, the four constant, delta H, delta S, and Fs, and also C mid values. That one. Yeah, this is for the correlation for the region of alpha plus beta. And for the alpha and the beta, and I think since the curve, you can see the curve are more or less similar. So we are using the same formula as a correlation model, that one, so in the equation 2, that one. So as you can see from this is for both absorption and desorption process. As you can see from this equation, it has 3 variables: concentration, pressure, and temperature. and also you can see there are 4 constant parameters: A, gamma, V, and H. So if we have the measurement data, that one, and we can create out this constant, that one, so that it can be used for different temperature, pressure, and concentration to predict the profile for the alpha and the beta regions. That one, yeah. So for the critical point, that one here, so we also have predicted the critical point for the transitional DOM curve, that one, yeah. So as we know, this for the midpoint for the each isothermal line in the alpha plus beta region, the absorption pressure can be calculated by using this formula. And the desorption pressure at the same temperature, the desorption pressure can be calculated by this formula. So we have already obtained the delta S and the delta H from previous correlations, that one. Yeah, so what we assume, so you can see that if these 2 pressures are the same, normally if the temperature is less than critical temperature, the absorption pressure is larger than the desorption pressure. So with the increasing of the temperature, that one, so the difference between the absorption pressure at same temperature, the difference between absorption pressure and the desorption pressure will be reduced. So on the point of the critical temperature, the absorption temperature and desorption temperature will be the same at the same temperature of critical temperature. So from then we can find out the critical temperature for this particular metal hydride alloy, that one, yeah. So it can be calculated using this formula, that one, yeah. And correspondingly, we can calculate out critical pressure for this metal hydride alloy by using equation 6. So after that one, so once we have the correlation formula for these 3 regions, and the crossing point can be calculated out. When we connect this the crossing point, that one, between 2 regions, we can find out the transitional DOM curves, which is presented with dot line and with the critical temperature on the top of this dot line, that one, yeah. So we assume this curve is a symmetry parabola shape, that one, yeah. So we can using this formula to calculate out these DOM curves, that one, yeah. So once we know the concentration, we can immediately find out the pressure. So this is the formula. So once we have the measurement data, so we can create out 3 coefficients, A1 and A2 and A3, and then obtain this transitional DOM curves, that one, yeah. So as an example, so we select the 4 metal hydride alloys and then by using what we have developed a correlation model to create out the coefficient for each correlations. So this 3 metal hydride alloy, including I think the 1, 2, 3. And this first 2 is used for the cooling system. That one, yeah. And you can see the tested isothermal range with different temperature range, that one here. And the last 2 is what we have identified for our high temperature metal hydride heat pump, that one, yeah. And we found out from the literature, that one, yeah, have the measurement range at different temperatures, that one, yeah. So once we have this measurement data, and we have already developed the correlation formula, so we can create out the correlative parameter for each correlation models, that one, yeah. And then we can draw the whole PCT phase diagram for each reactor for both absorption and the desorption process. And here is the result. You can see the correlation and also the measurement. The correlation is solid line. The measurement are represented with the different symbols that here. And you can see clearly the 3 regions, alpha and alpha plus beta and beta. And also you can also find out the critical point and also the transitional DOM curves that one here. So you can see, and in the alpha and the plus and the beta region, that one you can see the correlation is quite close to the measurement. And for the alpha and the beta region, I think the area is slightly larger than that of those of alpha plus beta region, but they are quite close. That one, yeah. So what I want to say that one. So based on this correlation model, so it can be used to depict and predict the whole overall PCT phase diagram for a particular diagram. We don't need to do the extensive and measurement to obtain this. We just utilize this correlation model to predict. And this is for this particular metal hydride alloys we found from the literature. And this is for the correlation, the comparison between the correlation and the measurement for that second metal hydride alloy for both absorption and the desorption. Again, you can see the correlation model is quite close to the measurement. And so by using this correlation model, we can predict the whole PCT phase diagram for both absorption and desorption. This is the second alloy, and this is the third one. This one is used as the high temperature metal hydride reactor for our high temperature metal hydride heat pump system. So you can see the correlation is match quite well with the measurement that one, yeah, and it can predict and for different temperature and the pressure and the concentrations. And the third one is the last one is for the this metal hydride alloys, which used as the metal hydride alloy for the low temperature metal hydride reactor. And you can see there are 4 temperature range for this particular metal hydride alloy. And again, I think the correlation match quite well with the measurement. So then I think, and we have theoretically characterized the metal hydride alloys, which will be used in our proposed proposed metal hydride heat pump system, and also it will be used for our future modeling development as well. And to apply this correlation model into actual system modeling, so we then develop a high temperature metal hydride heat pump system model. And see this, you have seen a similar system layout and the cycle from my previous slide, but here is slightly different. What you can see the difference is the heat output temperatures. So previous slide, we have only one temperature heat output. Now I think because this is the heat pump, so it's not necessary to only have one temperature heat output. But here we can have 2 different temperatures heat output. One is TM1 and TM2 here. So if this temperature is larger than the low temperature heat source temperature, so this heat output will both be useful for our overall heat output. That's one. Yeah. So this is the system layout is slightly different from previous slide. So we have developed this system model, that one, and integrate our correlation model in the model, so that in this system model, so that the system model can predict accurately of the system performance. So, and this is just to give you some brief description about the modeling development. So you can see the calculation of the heat input and the two heat input, QH and QL, and also 2 heat output. For each heat transfer, you can see it consists of 2 parts. One part is for the reaction. You can see the reaction entropy here. This is from the correlation model. And also there is another heat transfer, which is called sensible heat transfer. Just the heat directed from low pressure to the high pressure. So this is the heat input. For other heat transfer, you can also calculate it with a similar method, which includes both reaction heat and also the sensible heat. And apart from the reactor entropy, you can also see there are some concentration difference, delta C1 and delta C2 here, which are calculated by using these 2 formula. So this will cover the maximum maximum concentration change for both high temperature reactor and also low temperature reactor. And this concentration change can be calculated out based on the pressure balance and also the mass balance of the system. So for the pressure balance, you can see here, we calculate out the high temperature pressure and also high side pressure and also low pressure side. So after finish of the desorption process from high temperature process, high temperature reactor, and it will be received by the low temperature reactor, by the low temperature reactor on the high pressure operation. That one, yeah. So after the high temperature reactor finish its desorption process, we can calculate out its pressure. And in the meantime, that one, on the other side, that one, the low temperature reactor finish its absorption process. So once this pressure is the same, there's no hydrogen flow from the high temperature reactor to the low temperature process. So we can set up this pressure balance. Similarly, for the low pressure side, once the low temperature reactor finishes its desorption process, that one, yeah. And in the meantime, the high temperature process reactor will finish its low pressure absorption process. So there exists pressure balance at the end of desorption process for both high and low pressure side. That one, yeah. And there also exists the mass balance. That one here. So the maximum hydrogen desorption from the high temperature reactor will be the same as the maximum absorption from the low temperature reactors. That one, and the total hydrogen capacity for each pair of reactors will be the same for the whole system. So based on this equations, that one, yeah, the whole system model will be developed so that we can predict the whole system process at different heat source and different high temperature and low temperature heat source temperatures. That one, yeah. So we just give some examples. You can see these equations, we utilize some correlation parameters from what we discussed previously during the process of the characterizations. Yeah. So here I just give you some simulation results. The first one is the heat input variation with the high temperature heat source and low temperature heat source. That one. What you can see with the increase of the high temperature heat source temperature, the heat out input will increase. That one increase. This is because the increase of the heat input for the sensible heat transfer between the high pressure side and low pressure side. And also, if you have a low temperature heat source input, that one, the heat input for the whole system will increase as well. And when the heat source temperature increase much higher than, for example, 200 degrees, you can see a slightly decrease for the heat input. It's because of when the heat source temperature reach to the critical temperature, that one, yeah, the hydrogen absorption capacity will be decreased, which will affect the heat input to the high temperature heat reactor. And the right side is the heat output variation with the high temperature heat source temperature and the low temperature heat source temperatures. But you can see the trend is just opposite that one. Yeah, when you increase the high temperature heat source temperature, and you can see the heat output is decreased. So together, you can see here, when you increase the heat source high temperature heat source temperature, you can see the heating COP will be decreased. That one, yeah. So one is increased, one is decreased. Overall, the heating COP will be decreased. That one, yeah, like this. So the higher, so I think this simulator is similar to the absorption heat pump system. If you have high temperature heat source temperature and low temperature and low heat source temperature, that one, yeah, so that the COP will be decreased, that one, yeah. And this is an interesting result. We found out, we calculated out the heat output temperature, two heat output temperature. One is TM1 and TM2. That one, yeah. So what we found out that one, if the high temperature heat source temperature is lower than a specific value, for example, 185 degrees C, so one heat output temperature actually is less than the low temperature heat source temperature, which will not be useful in practice. So we want to have both heat output temperature higher than the low temperature heat source temperature. So that's why for this system, so what we found out, the heat source temperature should be higher than 185 degrees C, so that the heat output temperature should be useful, which are higher than the low temperature heat source temperature. So this I just give you some simulation result here because of time, and here just some prediction for the pressure for the high pressure side and some pressures for the low pressure side at different high temperature heat source temperature and low temperature heat source temperature. You can see the pressure. The high pressure is about maximally 15 bar, and the low temperature is less than 5 bar. I think the whole system will operate at a safe mode. So because of the low operating pressures in the system. And here, and I give some conclusions here. So one metal hydride pairs has been identified for the high temperature metal hydride heat pump. And a crazy model of PCT phase diagram has been developed to characterize any metal hydride alloy based on limited measurement data. A thermodynamic model of a high temperature metal hydride heat pump has been developed. The model can be used for the optimization of system design and optimal operations. And for the future work, so we just list some future work in this slide and complete and commission the test rig. So hopefully it can be complete by end of September this year. And develop control system and use test result to validate the theoretical models. And optimize design of reactors using CFD modeling and scale up designs to 4 kilowatt thermal capacity. Okay, thank you for your attention. Thank you.